Hi, and welcome to Module 1 of Lecture 4. This is the last lecture in this course, and it covers variation multiple regression specifications, which you might use when you want to run a multiple regression of the kind we talked about in Lecture 3, but for various reasons, whether you have a more complex specification or you violate some assumptions, you can't do so. The first version we're going to talk about here is the interaction term. You use interaction terms when you have situations in which you believe, for whatever reasons, that the effect of some variable x1 on y is itself affected by another independent variable x2. We say sometimes instead that x2 conditions the effect of x1 on y. For example, you might think that the effect of education on turnout is conditioned by or affected by income or gender or ethnicity. In these cases, we don't believe that the effect of education on turnout is a constant over all people, but rather it itself depends on other factors. So the way in which education affects turnout will itself depend on other factors. This is decently common in most of the stuff we deal with in social science. We don't think these so-called treatment effects are constant necessarily. They might be heterogeneous or vary across populations in different ways based on other observable or unobservable characteristics. To use interaction terms, the simplest way to do this, and there's more than one way to do this, but the simplest way to do this is to simply add another term to your regression that includes the product of the two independent variables times a new coefficient. So for instance, in the second bullet point here, we have y equals alpha plus beta 1 times x1 plus beta 2 times x2 plus the product term beta 3 times x1 times x2. This is a sort of standard form for an interaction term when you have two independent variables and you think that one affects the other one. Note a couple of things here. One, you must include all constituent terms when you are testing for interaction. By constituent terms, I mean all the individual pieces of your interaction product term. So for instance, if I had an interaction of just a bivariate regression, y equals alpha plus beta 1 times x1, and I wanted to add an interaction because I thought x2 affected the way in which x1 affected y, then I couldn't just add the beta 3 x1 x2 term. I'd have to also add the constituent term beta 2 times x2. Second, note whenever I'm saying that the effect that some variable 2 affects the way in which x1 affects y, I'm also effectively saying that x1 affects the way in which x2 affects y. We'll get into a little more in the problem session at the end of this lecture. Okay. To interpret the effect of x1, we have to go back to what we discussed at some length in the differentiation module, which is we are trying to understand the rate in which the way in which x1 affects y, holding all other variables constant. In this case, if you were to do that, you would look at this equation, to remind you from that module, and say, okay, well, x2 is constant, so we have a constant out front. The derivative of that is 0 from the definition of the derivative. This beta 2 x2 is also constant, so that derivative is also 0. Beta 1 is a constant. Beta 3 times x2 is also a constant. So we have beta 1 plus beta 3 times x2 all times x1. The derivative of x1, as we saw in the previous differentiation module, was 1. That leaves just a constant out front, beta 1 plus beta 3 times x2. And if that was way too fast, which it probably was, please feel free to go back to the differentiation module again and take a look again, and it might make more sense there now, having seen this as well. So this is the derivative, and what it says is the effect of x1 on y, as captured by this derivative, holding x2 constant, is a constant coefficient that was originally multiplying x1 plus another coefficient times the value of x2. So the value of x2 actually affects the way in which x1 affects y. So we have the effect of x1 on y is conditional on the value of x2. We'll look at this a little more graphically also in the problem session at the end of the lecture. Okay. Another thing we discussed briefly was possible nonlinear effects. A nonlinear effect is when your data displays some nonlinear dependence. So instead of a straight line, you think there might be some kind of curvilinear relationship. The example we looked at a couple times was of sleep on grades. As sleep increased, you increased your grades on average, but after a while, when sleep got too much, grades started decreasing. There are lots of ways to get at that kind of behavior. The simplest way and most common way in the literature is to simply add higher order terms to your regression, higher order polynomials. So instead of just alpha plus beta 1x, we also add beta 2x squared. In some situations, we might want to add cubic terms, x cubed. We do that sometimes in IR situations where we're looking at time dependence. To interpret this, we again go back to what we talked about in differentiation. You consider the marginal effect of x on y, and this derivative is going to be beta 1 plus 2 beta 2x, because the derivative of x2 is 2x. So now the marginal effect of x1 and y is itself dependent on the value of x. So again, notice how the value of x, the effect of x on y is affected by the value of x, so it changes as x increases. And we'll look at that a little bit graphically at the end of this lecture as well. Okay. Another situation in which you have a sort of variant regression specification is when you have time series. In time series, your variables often display trends in time that can lead to spurious causation. So for example, since World War II, there's been a growth in golf, the rate at which people play golf and the rate at which they get divorced. Now you could posit some kind of relationship causally, but there might also be some kind of spurious causation occurred by some general trend over time in the increase in both of them, and there's no correlation between the two of them. That leads to spurious causation because it is the dependence on time that's driving both increases and not any kind of causal relationship between the two of them. Or it might be the case that if you have variation in your data across time, then an event at some time t might be dependent not only on contemporary independent variables, but on ones in the past. Problem is, if you just include a whole mess of variables at previous times, as well as the ones presently, you can get multicollinearity, which is a thing we discussed in the matrix last couple modules when we discussed in the previous lecture, when you have two different independent variables that are too closely related or too closely correlated. In those situations, we saw in the matrix module that you get a determinant of 0, you can't invert a matrix, you can't calculate your coefficients. And again, if that was way too fast, which it probably was, you can go back to the matrix module, and maybe that'll also make a little more sense and or be a little more relevant to what you're thinking about, because this is where it comes up. It is also not clear in this case how many lagged variables you want, right? How far back in the past do you actually want to include when you do this kind of thing? There are lots of solutions to this problem as well. Whole classes are taught about time series analysis. Two common differences, though, I'll mention here. One is to difference your variables, and another is to include lag-dependent variables. To difference your variables, you transform your y's and your x's, your dependent and independent variables, to differences. Here, this is a capital delta, means change usually in most applications, and says the change in y variable is defined as, this 3 lines means defined as, y sub t, so the y at time t, minus the y at the previous time step. This is a first difference. You do the same thing as well for x. Difference in x is defined as xt minus 1. So the first difference in x. Using differences eliminates the dependence on everything beyond the immediate changes. The immediate change in y is caused by the immediate change in x. Because of that, you need a theoretical reason to want to do this. But you see this kind of specification pretty often. The other thing you see pretty often is a lag-dependent variable. Now you make your dependent variable y at time t a function of the same dependent variable at yt minus 1, so at the previous time, times some coefficient lambda, this is lowercase lambda, plus the other stuff that mattered at time t. So plus the constant, alpha, plus beta times xt, which might be a series of independent variables t. And here, you should note that these x's can be individual points. They could be whole vectors, or in this case, matrices of multiple independent variables. So this is saying we're making basically the previous period's dependent variable into another independent variable by lagging it. A lagged variable is one from the previous period or some previous period. What this does effectively is it allows the dependent variable to depend on all previous independent variables through their effect on the lag dependent variable. To see how this works, note that y of t minus 1 recursively is going to be a function of y of t minus 2 plus beta x of t minus 1. So y of t automatically becomes a function of x of t minus 1 that way, and then so on all the way down to the beginning of time. So y of t is going to be a function of all the x's through all time. However, if lambda is less than 1, then the past lags will have reduced effects because they're all multiplied by lambda, which is less than 1. The bigger lambda is, the more the effects of past history are on y of t. If lambda were 0, then there'd be no effect at all of the past on y at time t. So the lambda parameter lets you sort of tune the amount of past history that is relevant for prediction of the present dependent variable. Okay. So those are two of them. The next module we're going to discuss regression with dummy variables as another variant specification. Thank you.